In this episode, we will talk about DeCLIP, decoupled learning for open vocabulary dense perception.
Right. So let's think about how computers, well, see things. The traditional ways we get them to do things like object detection finding and boxing items in pictures, or image segmentation, which is much more detailed, outlining every single object pixel by pixel. These methods are good, really good in some ways.
But they have a big limitation, don't they?
They absolutely do. They usually work with a fixed set of categories, like they know car, person, dog, but maybe not aardvark or a specific type of rare flower. If it's not in their predefined list, they just don't see it.
And that's obviously a problem in the real world, which is full of, well, everything.
Exactly, which is why there's been this big push towards what we call open vocabulary methods. The goal here is much more ambitious. Systems that can spot and segment objects from any category, even ones they've never been specifically trained on.
And the key to that is language, right? Using text descriptions.
Precisely. By connecting the visual understanding to language, these models can generalize way beyond their initial training data. It's a powerful idea.
And a really foundational model for this is CLIP, contrastive language image pre-training.
That's the one. CLIP is designed to learn the relationship between images and text. It has two main parts: an image encoder to process the visual side, and a text encoder for the language side. And for this deep dive, we're specifically looking at versions of CLIP that use a vision transformer, or VIT, as the image encoder.
VIT. Okay, vision transformer. How does that work differently?
Well, instead of using convolutions like older methods, VIT basically chops the image into smaller patches, treats them a bit like words in a sentence, and then uses this mechanism called attention to figure out how these different patches relate to each other and to the overall image content.
Okay, so CLP has these two encoders, image and text. How does it actually learn to connect them, this vision-language alignment?
The core idea is contrastive learning. During training, it sees lots and lots of image-text pairs. For a matched pair, say, a picture of a cat and the text a fluffy cat, it tries to make their representations really similar. It does this by maximizing the cosine similarity.
Cosine similarity, that's like measuring the angle between their feature vectors. Closer angle means more similar.
Exactly. It measures the similarity between the image's global representation, which is often captured by a special CLS token. Think of it as a summary token for the whole image, and the features from the text encoder for the matching description.
And for pairs that don't match, like the cat picture and text a car.
Then it does the opposite. It pushes their representations apart by minimizing that cosine similarity. So it learns this goes with this and this doesn't go with that over millions of examples.
Makes sense. It learns the connections by contrast. So CLIP is great at this high-level image-text matching. Why can't we just, grab the features it learns for images and use them directly for those detailed tasks, the dense prediction stuff like outlining the cat's whiskers?
That's the million-dollar question, isn't it? And it turns out it's not quite that simple. While CLIP's global understanding is strong, if you try to use its internal, more localized image features, the ones corresponding to those image patches directly for dense prediction tasks, the performance is often, well, not great. There's something about those dense features that isn't quite right for fine-grained tasks.
Okay, so that leads us right to the core problem this research is tackling. Can we somehow take CLIP's features, maybe disentangle them, separate them out somehow?
Right, like teasing apart different strands.
And then apply different training signals or guidance to these separated parts. The idea being to create features that are better for both recognizing what's in a patch and understanding its spatial context, all within the same basic CLIP structure to boost that dense prediction performance.
Exactly. And that's where DeCLIP comes in. Decoupled learning for open vocabulary dense perception. It's proposed as a general method, importantly, an unsupervised fine-tuning method.
Unsupervised, meaning it doesn't need a whole new set of labeled data for segmentation or detection to learn this.
Correct. It refines the existing CLIP model using knowledge distillation, basically learning from CLIP itself and other pre-trained models to improve two key things about CLIP's local features: their discriminability, how well they distinguish different things, and their spatial consistency, making sure features for the same object look similar even if they're in different parts of the image.
And the core idea, you said, is decoupling, separating things out within CLIP's attention mechanism.
That's the heart of it. DeCLIP takes the self-attention module, which is how the VIT processes information by letting different image parts attend to each other, and sort of splits its function.
That's it how.
It decouples the features into what they call content features, aimed at local discriminability, and context features, focused on spatial consistency. And crucially, it allows these to be learned or refined using different guidance, different teacher models, separately.
Okay, so in this deep dive, we're going to unpack exactly how DeCLIP does this decoupling, what this weird proxy token thing is that they found in CLIP, and look at the proof of the experiment showing it actually works better for open vocabulary detection and segmentation.
Sounds like a plan.
All right, let's start by digging deeper into why standard CLIP struggles with these dense tasks. You mentioned the self-attention mechanism and the vision transformer.
Right. So in the VIT architecture used by CLIP, especially in the later layers, you have these self-attention blocks. Inside each block, you essentially have three key components derived from the input features: queries, Q, keys, K, and values V.
Q, K, V. I've heard those terms.
Yeah. Think of it like this. Each image patch feature sends out a query. It compares this query to the keys of all other patches to figure out how relevant they are. This comparison gives you an attention score.
So high attention means pay more attention to this other patch.
Pretty much. Then these attention scores are used to weight the values of all the patches. So you get a weighted sum of values, which becomes the output feature for that initial patch. It's a way for each patch to incorporate information from other relevant patches.
Okay, and the CLS token we talked about, the global image summary.
Right, that's typically the very first token in the sequence going through the transformer. After all the attention layers, the final embedding for this CLS token, let's call it Z0, represents the whole image for the language contrastive task.
And the other tokens?
Yeah.
The ones from the image patches?
Those are the rest of the sequence, Z1 up to ZHXW, where HXW is the number of patches. If you take these patch embeddings after the final attention block and reshape them back into a grid, you get what we call dense feature representations, a feature vector for each patch location.
So these dense features are the ones that ideally we'd use for segmentation or detection, but they have issues.
Exactly. And the researchers identified a really interesting phenomenon, especially in the deeper layers of CLIP, say, after the 9th layer out of 12. They called it the proxy token phenomenon.
Proxy token, what does that mean?
What they observed, and you can see this in figure 3A of their paper, is that the main CLS token, the one summarizing the image, starts paying less attention to the actual main objects in the image.
That sounds wrong. Shouldn't it focus on the main objects?
You'd think so, but instead it starts directing a lot of its attention to specific tokens, specific patches that are actually in the background of the image. These sort of become proxy tokens.
Weird. Does this happen just for the CLS token?
No, that's the other strange part. The individual image patch tokens start doing it too. Even a token representing part of the main object might start paying high attention to these same background proxy tokens, regardless of where it is in the image.
So the whole network gets sort of fixated on these random background spots. Why would it do that?
The paper suggests a possible reason related to the VIT architecture. Unlike convolutional neural networks like ResNet, which naturally downsample the image and create more abstract features in deeper layers, VITs mostly keep the same number of patch tokens throughout.
Okay.
So the hypothesis is that maybe these background proxy tokens become like information hubs. They might aggregate important context from many other patches, allowing the main CLS token to get the global overview it needs for the image text matching task CLIP was trained for. It might be a workaround because VITs don't have that built-in spatial pooling like CNNs.
Ah, so it's like an emergent strategy in the VIT to get the job done for image classification, but it has side effects.
Precisely. And the major negative side effect for dense prediction is how it messes up the relationships, the correlations between the actual image patch features. Look at figure 3A again. They show what happens if you pick an anchor token, say, on a bird. Then they shift the anchor to the branch next to it. You'd expect the attention to shift to other parts of the branch, or maybe the bird. But no, the attention still focuses heavily on those same background proxy tokens.
So patches that are clearly related semantically, like different parts of the same branch, aren't strongly connected in terms of attention because everything's looking at these proxies.
Exactly. There's a lack of correlation between patches that should be correlated because they represent the same thing or related things.
And that lack of correlation is bad for dense prediction.
Very bad. For something like segmentation, you absolutely need features that are consistent. If one part of the cat feature looks totally different from another part of the cat feature just because they paid attention to different proxy tokens, it's incredibly hard to group them together accurately. You need both local discriminability, telling cat from dog, and spatial consistency. All parts of the cat look like cat.
Which explains the results they show in Figure 2a, where using raw CLIP features directly gives pretty poor results on COFIO for things like region classification and segmentation.
Right. It highlights this fundamental mismatch between what CLIP optimizes for globally and what's needed locally.
Okay. Now, you mentioned other models, these Vision Foundation models, or VFMs, like Dino and SAM. How do they compare regarding this proxy token thing?
That's a key point. Models like Dino, which uses self-supervised learning to learn visual features, and SAM, the segment anything model, which was trained on tons of segmentation data, they generally don't show this proxy token behavior. You can see the contrast in Figure 3b.
So their attention maps look different.
Yes, they tend to extract features with much better spatial consistency. If you look at their attention maps, you don't see that strong focus shifting to specific background spots. And importantly, if you move an anchor token, say from one part of an object to another, the attention correctly follows the semantic, meaning it pays attention to other parts of the same object.
That makes sense, given they were trained differently, maybe with objectives more focused on spatial understanding. So why not just try to make CLIP learn from these VFMs? Like distill the good spatial properties from Dino into CLA.
That's exactly what the researchers tried initially. They attempted to add a VFM distillation loss during CLIP's fine-tuning, basically trying to force CLP's features to correlate spatially, like Dino's features do, while also doing the self-distillation needed for good vision-language alignment.
Did it work?
Surprisingly, no. It actually hurt performance on region classification tasks. Table 1, row 2 shows this result. Performance went down.
Huh. Why would combining them make things worse?
The hypothesis is that the optimization goals might be somewhat conflicting. Learning strong spatial correlation, like Dino does, might pull the features in a different direction than learning the specific vision-language alignment that CLIP needs. Trying to push both simultaneously within the same undifferentiated feature space might create interference.
Which brings us back full circle to DeCLIP's main idea. Don't try to mix them directly, decouple them first.
Exactly. If you can separate the parts of the feature responsible for spatial context from the parts responsible for semantic content, maybe you can optimize them separately without them interfering.
Okay, let's get into the DeCLIP solution itself.
Right.
How does this decoupling actually work architecturally? You mentioned Figure 4c.
Right. So DeCLIP modifies the final self-attention block in CLIP. Remember the standard calculation. Q and K determine an attention map at TINC, which weights the values V to produce the output. DeCLIP rethinks this.
Rethinks is how?
Based on work showing CLIP's features do have some local semantic info, they decided to treat the query, Q and KK components, primarily as anchors for improving spatial consistency. And they treat the resulting dense features, let's call them X-dense, as the anchor for improving local discriminability.
So different parts of the standard attention mechanism are repurposed for these two distinct goals. How has the calculation changed? Equations 4, 5, 6 in the paper.
Okay, so they introduced two distinct feature streams originating from the input X to that final block. First, they compute a context feature, X context, just using a linear projection of X, proj QX. Think of this as pulling out the spatial relationship information.
Got it. One stream for context. What's the other?
The second is the content feature, X content. This is calculated by aggregating the original value embeddings V, but using a new attention map, which they call at context. And here's the crucial decoupling step. This atom context is generated only from X context itself. Specifically, it's softmax applied to X context multiplied by its transpose, X context, X context.
Whoa, okay, so the attention map used to create the content features is derived only from the context features, not from the original Q and K interactions.
Precisely. That's the decoupling. X context determines the semantic spatial relationships between regions, who should pay attention to whom, and that relationship map, at and context, is then used to pool the semantic information from the value embeddings, V, to create X content, which lives in the vision language space.
That's clever. By separating the calculation of the relationship map, context, from the application of that map to the semantic values, content, you can optimize them independently.
Exactly. Now, you can apply different guidance signals to X context and X content without them messing each other up, which was the problem with the earlier attempt to just mix VFM distillation into standard CLIP training.
So what guidance do they apply to each? You mentioned VFM and self-distillation.
Right. For X context, the goal is spatial consistency. So they use a pre-trained vision foundation model like DynoV2 as a teacher. They basically train X context to have similar spatial correlation patterns as the features from DynoV2.
Makes sense. Use the model that's good at spatial stuff to teach spatial stuff. And for X content, the semantic part.
For X content, the goal is local discriminability and good vision language alignment. Here, they use self-distillation. The teacher is the original pre-trained CLIP model itself.
Self-distillation. The model learning from itself. How does that work here? Figure 5 illustrates this.
Yes. It starts with image patching. You take the input image and divide it into, say, K smaller subregions or crops. Let's call this set of cropped images S.
Okay, chop up the image.
Then the student model, the DeCLIP model, being fine-tuned, processes the original full image to produce its X content features. Now, for each of those cropped regions in S, you need to extract the corresponding feature from the student's X content map. They use row I align for this region of interest align to accurately pool the features, Fs, that correspond spatially to where those crops were in the original image.
Okay, so the student gives local features, F, for the crop locations. What does the teacher, original CLIP, do?
The teacher's CLIP, which is kept frozen, its weights aren't changing, processes each of those small cropped images from S individually. For each crop treated as a standalone image, the teacher's CLIP outputs its global CLS token representation, FT.
Ah, so the teacher gives a global summary, FT, for each crop, while the student gives a local feature, S, from the corresponding region in the full image.
Exactly. And the goal of the content distillation is to make the student's local feature F similar to the teacher's global feature FT for that same patch. They use a cosine similarity loss, L content, equation 7, to minimize the difference between Fs and FT for all the crops.
Why should that help? Why make the local feature look like the global feature of a crop?
The intuition is that the original CLIP model is really good at understanding the overall content of an image, even a small cropped image, because of its massive image text pre-training. Its CLS token for a crop likely represents the semantics of that crop quite well.
Better than just pulling a feature from a map of the whole big image.
Potentially, yes. So by forcing the student's local features, FT, to align with the teacher's global crop features, FTP, you're essentially distilling CLIP's strong image-level semantic understanding down into the student's region-level features, making them more discriminative.
Okay, that makes sense. Leveraging CLIP's global strength to improve its local weakness. But you mentioned earlier this might not be enough for pixel-perfect segmentation.
Right. While this content distillation really helps with recognizing what is in a region, it's based on these, well, potentially chunky image crops. It might not give you the super fine-grained spatial precision needed to draw exact object boundaries pixel by pixel. That's where the context distillation comes in.
The context distillation using the VFM teacher like DynoV2, that focuses on the spatial relationships, the where.
Exactly. So again, referring to figure 5, the goal here is to transfer the good spatial properties from the VFM to DeCLIP's X context features. You feed the same input image to both the DeCLIP model, student, and the pre-trained VFM teacher, for example, DeFoV2. The VFM outputs its dense feature representations, XVFM dense.
Might need to handle different input sizes, right?
Yes, potentially. They often adjust input resolutions so that both models produce the same number of patch tokens, making the comparison easier.
Okay, so you have dense features from the VFM and the X context features from DeCLIP. How do you compare their spatial properties?
They compute something called a correlation volume for each. It's basically a matrix where each entry, right, is the cosine similarity between the feature for patch I and the feature for patch J. You calculate this matrix for the VFM features and separately for the DeCLIP X context features. Equation 8 shows the similarity calculation.
So these matrices capture the pairwise similarity patterns across the whole image for both models.
Precisely. And the context distillation loss, L context equation 9, is simply an L2 loss, the squared difference between these two correlation volumes. By minimizing this loss, you're forcing DeCLIP's X context features to mimic the spatial correlation structure learned by the VFM teacher.
Got it. Make the context features behave spatially like the VFM's features, and the final training combines both losses.
Yes. The total loss, L total equation 10, is just a weighted sum, L content plus lambda times L context. Lambda is a hyperparameter balancing the importance of improving semantic content versus spatial context.
Okay, that's a really clear breakdown of the DeCLIP mechanism. Decouple, then distill content using self-distillation and distill context using a VFM teacher. Now, the crucial part, did it actually work? Let's talk about the experimental results.
They really put it through its paces. Extensive evaluations on multiple open vocabulary benchmarks, object detection using OV-COCO and OV-LVIS datasets, semantic segmentation with the CAT-SEG framework on datasets like Cityscapes, Pascal VOC, COCO stuff, and also evaluating the raw features for segmentation.
Let's start with object detection. How did it stack up against baselines like FEIT and OVDQUO?
Significant improvements, especially on the challenging novel classes, the ones not seen during pre-training. On OV-COCO, Table 2 shows DeCLIP boosting FEIT by 3.5 and 1.9 MMP points on novel classes, depending on the setting. And against OVDQUO, the gains were even larger, 6.9 and 2.7 MMP on novel classes.
Wow, nearly 7 points in one case. That's substantial. What about LVIS, the long-tail dataset?
Similar story, particularly for the rare classes. Gains of 1.5 and 2.3 MAP with FVIT and 1.3 and 2.2 MAP with OVDQUO on those rare categories. It shows DeCLIP really helps generalize to less frequent objects.
Did they test transferring a model trained on one dataset to another?
They did. They trained on OVLVIS and tested directly on COSIO and Objects 365 without fine-tuning. Table 3 shows DeCLIP maintained its advantage, demonstrating good cross-dataset generalization.
Okay, strong results for detection. What about semantic segmentation, the pixel-level task? They used CAT-SEG as the base model.
Yes, with DeCLIP as the backbone feature extractor. And again, Table 4 shows really significant performance boosts across all the datasets tested. What's particularly impressive is that CAT-SEG using a VINT-based DeCLIP backbone.
The smaller VIT model.
Right, the VIT-B16 version. It performed almost as well as, or sometimes even better than, state-of-the-art methods that were using much larger encoders, like COMNEXT Large.
That's efficient. Getting top results with a smaller backbone?
Exactly. And when they did scale up to the VT Large DeCLIP, VDA L14, it set new state-of-the-art results on several benchmarks.
Very convincing. And the evaluation based just on VLM features, assigning pixels based on cosine similarity to text.
Even in that direct feature evaluation setup, DeCLIP came out on top. Table 5 shows it outperformed all the comparison methods in average MIU across 8 different segmentation benchmarks. It really confirms that the features themselves are more semantically meaningful and spatially coherent.
What about region classification? Did they test that specifically?
Yes, on the COCO panoptic validation set. Figure 6 shows the results comparing DeCLIP against RegionCLIP and CLIP-SELF. Using standard row-I-align or mask pooling, DeCLIP consistently achieved higher top-1 mean accuracy, MEC across different image resolutions.
So across detection, segmentation, and region classification, DeCLIP seems to deliver solid improvements. Did they show any qualitative examples, like visual comparisons?
They did. Figure 7 is quite informative. It compares attention maps from Dino, SAM, DNOV2, and DeCLIP. You can visually see how DeCLIP's attention focuses nicely on regions that are spatially close or semantically related to an anchor point.
And they felt DeCLIP distilled from DNOV2 looked best.
Yeah, their interpretation was that DNOV2 hits a sweet spot. SAM might not capture semantics well enough in attention, and Dino might be a bit too broad, while Dino V2 provides the right kind of spatial semantic guidance for DeCLIP.
Are there other visuals, maybe showing the proxy tokens or feature correlations?
Yes. In the supplementary materials, Figure 8 clearly shows that proxy token effect ticking in after Layer 7 in standard CLIP. Figure 9 visualizes feature correlations, highlighting how standard CLIP struggles with pixel-level consistency compared to DeCLIP. And Figure 11 is interesting. It shows attention maps on regular images versus stylized images, like paintings. DeCLIP maintains better semantic focus and granularity even on these out-of-domain styles, despite only being fine-tuned on COCO.
Those qualitative results really help build intuition for why it's working better. Lastly, did they do ablation studies, picking apart the model to see which bits matter most?
Absolutely. Several key ablations. They tested different ways to compute X context, Q only, K only, Q plus K, and found performance was pretty robust, maybe slightly better with Q or K individually. Table 7.
What about how many layers to fine-tune?
That was interesting. Table 8 shows region classification improved with more layers, but segmentation peaked around 6 layers. They chose to fine-tune all layers for their main results as a balance.
And the lambda parameter, balancing content and context loss.
Table 11 shows it's quite robust. Performance didn't change drastically within a reasonable range, so they picked lambda equal 0.25.
Did they try using a better CLIP model as the base, like EVA-SLIP?
Yes. Table 12 shows they used EVA-CLIP as a baseline. DeCLIP still improved performance on top of EVA-CLIP, suggesting the benefits aren't just from starting with a better CLIP, though EVA-CLIP's stronger pre-training certainly helped the overall numbers.
And crucial sanity checks comparing DeCLIP against other methods using the same EVA-CLIP backbone.
Right. Tables 9 and 10 confirm this, even when comparing CatSeg or ClearClip using EVA-CLIP versus DeCLIP, also built on EVA-CLIP. DeCLIP still provided significant gains. This strongly suggests the decoupled learning strategy itself is the key driver of the improvement.
That seems like a very thorough set of experiments validating the approach. So if we were to boil it all down, what's the main takeaway from this DeCLIP research?
I think the key message is that standard CLA, while powerful for global image text tasks, has limitations for dense prediction due to issues like the proxy token phenomenon affecting local feature quality. DeCLIP offers a really elegant solution by decoupling feature learning into content and context streams.
And then optimizing them separately using
Right.
targeted distillation.
Exactly, using self-distillation guided by CLIP itself for content, and VFM distillation guided by models like Dino V2 for context. This allows it to improve both local discriminability and spatial consistency without the conflicting objectives you get when trying to train them together directly.
And the proof is in the pudding. State-of-the-art results across the board on open vocabulary detection and segmentation benchmarks.
Yes, the experimental evidence is quite compelling. It shows substantial gains, especially for recognizing novel objects, and achieves excellent performance even with relatively smaller backbone models compared to prior art.
What do you see as the broader significance here? What does this tell us about building better vision models?
I think it highlights the power of disentanglement. Large models learn incredibly rich representations, but sometimes different aspects are tangled together. By finding ways to decouple these aspects, like semantic content and spatial context here, and optimizing them specifically for their roles, we can unlock better performance for more fine-grained tasks. It suggests a promising direction for improving multimodal models more generally.
It really makes you wonder, doesn't it? If decoupling works so well here for vision language models and dense perception, where else could this apply? Could we decouple different reasoning steps in large language models? Or disentangle different types of information in video or audio models? It feels like this idea of targeted, disentangled optimization might lead to some really interesting new architectures and training approaches down the line. What other hidden potentials in these giant models could we unlock by carefully pulling apart the threads? It's definitely food for thought.